Great. Well, first of all, thank you everyone for taking the time to attend today's session and to take part in the discussions that we'll be having later on. And just to let you know, we'll be recording today's session, which we'll release to participants afterwards. So I'm Lewis Hotchkiss, and I'm the Research Officer at Dementias Platform UK, and I'm just going to be giving you a brief overview of what today's session is about and what we hope to achieve with this working group. So after I've given a bit of a background in synthetic data and what some of the reasons are for using it, Emma Squires, who manages the DPUK data portal, will be giving a talk on how synthetic data can be beneficial for trusted research environments, but also what some of the governance challenges may be with using it in practice. Then our data scientist, Kafiat, will be explaining a bit more about the different methods for generating synthetic data and how we've been trying to develop a framework for generating and evaluating synthetic data within the DPUK data portal. Then I'll be going on to talk about how we can evaluate synthetic data to ensure it can be used for the purpose it's been made for and can be safely released from trusted research environments. And finally, at the end, we'll have a group discussion where everyone will be able to have the chance to participate, where we'll discuss the challenges of using synthetic data in practice and how we can ensure it meets certain guarantees for things like privacy. Now, we're from the Dementias Platform UK data portal, and Emma will talk about this more later on, but we're essentially a trusted research environment which brings together over 3 million participants from dementia-related cohorts. And essentially, we're interested in synthetic data as it enables us to continue to protect the privacy of our data for a number of different purposes outside of the TRE. One of these purposes is for training private AI models. And because we have such a wide range of multimodal data within DPUK, we've had lots of AI projects, with some of them having the potential for clinical implementation and deployment. So we need to ensure privacy is preserved in these models once they're let out. Now, a lot of my research focuses around responsible AI development in sensitive healthcare datasets, so that models trained on sensitive data can be deployed safely into real-world settings. And recently, DPUK was funded by DARE UK to set up an AI risk evaluation group to bring together members of the public, expert AI researchers, and data providers to be able to understand perspectives of developing AI in secure environments. As some of you attending today's session may have been part of that group, and this mainly focused around the privacy issues and how these can be mitigated. And from our workshop, we published our report, and we found that synthetic data was one of the better solutions for mitigating privacy concerns within AI models. And it was a method that researchers felt most comfortable with implementing into their research. So this is why we've set up this synthetic data working group as an extension of that AI risk group to investigate how we can effectively implement synthetic data in practice, but not just for privacy purposes, but also for improving robustness and mitigating bias in AI models as well. But in today's session, we'll mainly be focusing on the privacy aspect, as that's what we're most interested in as a TRE. And of course, synthetic data has other purposes other than for training AI models to be private. We're also interested in the use of synthetic data for things like federation applications or for researcher training. But all of these different purposes generally have the same governance challenges around privacy which need to be overcome. So the purpose of this group is to understand the different use cases of generating synthetic data and how we can effectively evaluate this data to ensure privacy. And more crucially, we want your input to be able to help develop guidance and governance on supporting synthetic data in secure environments. Now, we have a wide range of people here today. Some of you may be researchers, some of you may help run TREs, and we also have some members of the public here as well. All of opinions of which are really crucial to helping to address the challenges in synthetic data. So we hope that all of you in this group will help shape this work by taking part in the discussions later on and collaborating on projects with us as well. But before we move on to the other talks today, I thought I'd give a brief overview as to what synthetic data is so that everyone can have an understanding of what it is, how it's generated, and why we might want to use it. So I'm going to give a very simple explanation of synthetic data using Lego characters as an example. So let's say we have a real data set of characters with 4 characteristics. We have leg color, body color, gender, and hairstyle. Now, we may have some correlations which exist within this data, say between gender and hairstyle or between color combinations between the body and legs. And we want to be able to generate synthetic data to create synthetic versions of the real data so that they resemble the ones in the real data set, but not match them exactly. So we try to keep the same sort of features and correlations in the synthetic version compared to the real version. Now, if we want good quality synthetic data, we tend to want to have the distributions to match and the correlations to match as well in the synthetic version. So say if blue was the most common color in the real data, we might want that roughly to be the case in the synthetic data as well. So these synthetic versions aren't exact copies, but the overall sample attempts to roughly have the same distributions and correlations for the features. So we'd still be able to ask the same sort of questions like which color is most popular, or what's the association between two features without actually having to access the real data. And so that we have that sort of privacy preserved within that, so that we're not using the real attributes of people. But because it still matches the group correlations and distributions, we can still use it to have meaningful analysis of that data. And there's a few purposes why we'd want to generate synthetic data. One of them is to increase sample sizes of minority classes. In the real data set, we may have very few cases of female characters, for example, which can make it hard for AI models to be able to learn about these samples. So we can use synthetic data to balance these groups to ensure the sample is fair. Now, if you've looked at any image generation models like OpenAI's, you can see that there's certain biases which are carried out in this synthetic data, and so they have to be mitigated sometimes. So if you asked it for an image of a teacher, it would almost always provide an image with a white female because the image data it was trained on mainly contained images of white females when you search for teachers. But they implemented mitigations into their synthetic data so that they were able to generate more representative samples of that data. But as well as mitigating bias in AI models, we can use it to mitigate privacy. So if you're a unique individual within a data set with very unique features, then you're a lot easier to identify because you're very unique in that data. But by creating lots of synthetic samples around that data point, it makes it more difficult to determine the actual features for the real sample. And there was a paper which looked at this re-identification risk in anonymized datasets, and they found that they were able to re-identify a majority of individuals just by using a few common attributes about them. So we can see here with an example of some attributes about an individual put into this statistical model, how the more attributes we have about a person, the higher the likelihood of re-identification is. And so, we can typically reduce this risk by removing certain features about an individual, but we can see the more features we have about a person, the higher that risk of re-identification because the more unique they are. But we also have the problem of higher re-identification in minority groups. So if we change just one of these attributes, the marital status, from never married to same-sex partnership, we see this risk of re-identification jumps from 2% to 82% because that individual is more unique in that data set. So, you may not have to be worried if you're matched the general populations of a population, if you have attributes which are more common in that population. But if you're in a minority group or someone with rare conditions, then you're much more likely to be able to be re-identified in a data set because you're more unique. And we can see how the combinations of variables, by changing this attribute, the risk of re-identification remains relatively high for all of these combinations compared to never married same-sex partnership. So when we're generating synthetic data, there exists a trade-off between privacy and utility, and this is sometimes often difficult to manage. But essentially, if we want to create more private data, we sometimes lose the utility of that. And this is because the more private you get in datasets, the less information you have to have meaningful, useful analysis. And this is the same for synthetic data. The more we move away from the real sample, the less quality we have and the less usefulness we have for creating meaningful results. So if we're wanting to create synthetic data for AI models, we tend to want to have quite good utility. So it's difficult trying to find the balance between these two things, the utility and privacy, to find a good trade-off. So typically, if you have very high private data sets, then you tend to lose the distributions and the correlations of the features so that they no longer match. So the more you move away from the real distributions and correlations, the less useful that data becomes. And so this is a big problem that we have to overcome if we want to use synthetic data for AI applications. But if we want to use synthetic data for researcher training or other applications, then this may not be as much of a concern. But if we look at the support distributions of the real and synthetic samples, we can see sort of the overlap of certain points here. We have outliers in the real data, and if we're generating private data, we often don't want to include outliers because they could be highly identifiable. But if we wanted good utility, we may want to include it for the analysis. What we don't want when we're generating synthetic data is these unauthentic high-quality samples, where you generate synthetic data which matches the real space, but is too similar to one of the real existing data points, that it's basically the same and not different at all. So it doesn't preserve any privacy in that aspect. What we also don't want is lots of noisy samples. So when we're generating private synthetic data, we might get points which exist outside of what exists in reality. And so you lose those correlations between attributes and the distributions. What we ideally want when we're generating synthetic data are these authentic high-quality samples, which match what's in the real space, but it's far enough away from the real samples that it's not identifiable to the original data. So when we're generating high utility data, we might get spaces like this, where there's lots of synthetic data points which are close to the original data points. So we get lots of these unauthentic high quality samples. If we're generating high privacy synthetic data sets, then we get more of the case of lots of noisy samples which don't match what's actually going on in the real space. So again, it's finding the balance between these two things so that when we're generating synthetic data, we get a good balance between the privacy and utility aspect. So hopefully that gives you a bit of a background on synthetic data and some of the reasons why we might want to use it. And I'll now pass you on to Emma Squires, who will discuss the benefits and challenges of synthetic data in a TRV. Please feel free to ask questions in the chat throughout this session, and we'll try our best to respond. And after the talks, there'll also be a chance for discussion and questions as well. Thank you.
With me. Okay, so there we go. I'm all set up. Right, I haven't got beautiful slides like Lewis. I've just got normal regular person slides, so I apologise in advance for that, but I'll hopefully do the best I can. So as Lewis said, I'm Emma Squires. I run the Deep UK trusted research environment and manage its everyday operations and development projects. And I'm just going to give an overview. As Lewis said, we've got quite a wide range of people on the call, so I'm just going to go through what trusted research environments are, what they're aiming to do, and what the utility of healthcare data is, and how synthetic data will be of benefit to us. So throughout a person's lifetime, there will be large amounts of health data collected about them. So every time someone visits a GP or a hospital, gets tests done, they prescribe medication, all that information is captured by computer systems and transferred to databases. So, which was great. We've got all this digital information about people. However, those databases are not very well connected. So you'll have things like their genetics information is completely separate to their emergency room data. So for being able to bring that data together has loads of utility, particularly around improving patient outcomes and identifying patterns and trends that could be used to improve patient care. Can also look at disease monitoring and public health planning, and COVID was a really good example of the rollout of a massive vaccination program and monitoring of how effective that program was, and the ability to have the data and use that data was really imperative to that. Can also be really useful for research and innovation, and that's a lot of research is about looking at what the risk factors for diseases are, how to diagnose diseases earlier, and also to make sure that there's effective treatments and how those treatments are working across a population. And that healthcare data can also be fed into health policy development. So data-driven insights can support policymakers to make decisions about resource allocation and identifying areas needing further funding. So there's real utility for this data, but how that data is used is really important, because there's also concerns around access to that data. The data is public data. It's about people and it's their data. So we want to use it for the public good, but we need to make sure that that data is safe and used only for what people wanted it to be collected for. So health data often contains sensitive and personal information. So there's stuff in your health records that you would not want to share. So it's making sure that we do not release that data out into the public, that we create it in a secure environment for access. We don't want anybody just accessing the data. We don't want to make sure that it's used appropriately. We make sure there's good regulatory compliance, that it's abiding by GDPR laws, etc., and that we're doing this as safely as we possibly can. So what is a trusted research environment then? So these are what's being proposed as being set up to handle this data and allow researchers access. So a TRE is a highly secure computing environment that provides remote access to health data, and approved researchers can access that data. The data is stored in large databases, and virtual computers sit on top of the database. And approved researchers can be given access to a virtual computer, and then they can access that virtual computer via their own computer or laptop. In the virtual environment, they can then analyze the data, but they cannot remove it from the trusted research environment. They can use the software in the virtual environment to analyze the data, but the data always remains safely inside that environment. So this slide just shows how Deep UK is set up as a TRE. There's many TREs across the UK. They're all slightly different, but the majority are very similar in nature to this. We abide by the 5 safes that have been proposed by HDI UK to ensure that that data is always protected. So only de-identified data is brought into the TRE, so all identifiable information is removed. So it means that the researcher is only accessing de-identified data. But those demographics are stored in a trusted third party so that we can link data sets across, healthcare trusts, across research studies that have been done, so that we can have rich data environments for the researchers to access. The data is then brought in. When it's brought in, it's stored on highly secure servers, and researchers apply to access the data. Those applications are reviewed by a study approvals panel to ensure that they are in the public interest. And if the project is it's decided to be in the public interest and approved by the panel, we provide a login access to a virtual desktop for the researchers to be able to access that data. Once the researchers carried out the analysis in those desktops, they can request that they take their results out. So we do not let data out. So we have data analysts that will review those file outputs to make sure that there is no data in there and that there is no privacy risk. There's no small numbers like Lewis was talking about earlier, that there's no outliers, that you cannot determine someone's privacy from it. And like I said, we cover the 5 safes off in that as well. So we make sure that only researchers that are part of an organisation access that data, that the projects only have the data that they need to carry out their project. We don't give out all the data, and that is carried out in safe settings. And we make sure that we use SERP infrastructure that is fully ISO 27001 accredited. We also make sure that the data is de-identified so that we can keep the data as safe as possible. And again, like I said, we review those outputs to make sure the data is never leaving as well. So this is just a little bit of background about Dementia's Platform UK, just to give an example of why, of the remit of a trusted research environment. So It's being funded by the MRC. It's in its second round of funding now. And the aim is to detect and treat dementia earlier than ever before. We've got over 60 data sets, and we have imaging and genomics data for about 3.5 million participants. And as we said, we allow researchers to access that data to do that research. We have over 445 active users. And this is just a quick dashboard snapshot of Deep UK and shows that we accept applications from across the globe. So this is, really huge project. There's great research going on across Deep UK. But you can see that it's a very secure, tied down environment. Everything happens inside the TRE. So why are we interested in synthetic data? And we really are, because data discovery is a big issue. You can tell somebody about the data, but they can't see the data, they can't touch the data. So to know if that data is the right kind of data for the analysis that a researcher wants to do, and what kind of research methods they should use given that type of data, is difficult. You're just going through a description of that data. If we had synthetic data, we could surface, I don't know, maybe the first 5 rows of a data set, which would give the researchers an idea of how that data is stored and what the structure of that data is. And this would allow them to write better applications. And you don't want somebody to come into a TRE, apply for the data, get the data, and it hasn't got what they want, or it's not in the right structure, or there's values that are missing. It would be really good to give them as much information as we can. And synthetic data would give them a snapshot of what that data set looked like. But it would also be really important in training. It would be great to have a training environment where researchers can come in and learn about using the data and run that learning inside a sandbox environment where they can, test algorithms and new methods and privacy preserving techniques on data that is very representative of the data that they'll be using when they have full access to the TRE. Again, algorithm development is really important as well. Whilst you're waiting for the governance to go through about whether you can apply for the access or not, you could be developing the algorithm ready on synthetic data. And then once the governance comes through, you can just deploy your algorithm and get your results. So it speeds up research as well. Federated analysis is really difficult because you can't see the data. You really are going on just a description. Even when you have full approval, you're not going to see the data. So being able to have a representation of that and to be able to develop your algorithms to be containerized would be really, really helpful for researchers. We also want to use, and Lewis made talked about it in his presentation about AI and being able to support AI, and having large numbers is really important. So being able to create synthetic versions of say, brain images will really enrich the data sets that we've got and allow better training of those models. And also, as Lewis mentioned, using them for privacy preserving. So if you train the model on synthetic data, the privacy risks are much, much less. And that's absolutely great. Sounds magnificent, but there's a lot of concerns about synthetic data as well. So the first is, how's the synthetic data going to be generated? There are many, many different ways to generate synthetic data, and it's all very complicated. And as a TRE manager, which one's the best method? Which one is appropriate for the use case for the synthetic data that I have? So, working that out and having that in a way that I can make a decision about what type of synthetic data generation tools to use is really important. Also, is it synthetic enough for the use case of staying inside the TRE, but just enriching a data set? We want very high fidelity synthetic data. But for releasing from the TRE for researchers to be accessed without approval, it would have to be very low fidelity because it needs to be as far removed from those people as possible to be completely private. So where's the boundary? Where's the difference? How do we assess how synthetic it is? And what does and who does the synthetic data belong to? If we're generating synthetic data from cohort data sets, and the data provider is a Whitehall study, if it's very low fidelity and does not represent that original data set, is it a new data set? Does it belong to the original cohort study? These are all governance decisions that really do need to be fleshed out before we can properly use synthetic data. Also, what about the public? It's their data that it's being trained on. Is it private enough? Should it be used in the way that we're talking about using it? And also, we need to talk to the data providers to say that we've taken this data set and we've got a synthetic version, and and talk them through that process and why we're doing it and what the reasons are. So how do we communicate this? How do we take these really complicated synthetic data generation tools and put them into a way that is meaningful for the data providers? Okay, so that's the end of my presentation. I'll pass you back to Lewis.
Thank you, Emma. So we're now going to go on to Kafayat, who will give a brief presentation on generation methods for synthetic data and how we've been developing a framework in Deep UK to support generation of synthetic data.
Hi, everyone. I'm Kafayat, data scientist at Deep UK. I'm going to be talking about the synthetic data generation framework. And this framework includes generation, evaluation, and optimization of the generation of synthetic data. So Lewis is going to talk about the evaluation bit later on in this discussion, while I will focus mostly on the generation and optimization aspect of synthetic data. So when it comes, the generation bit involves pre-processing and the automated setup of this initial process of the original data set, while the optimization aspect will focus more on the trade-off between having privacy or utility. Also, we also plan to have this framework as a Python package with a documentation on how to use it, as well as a user interface where user could generate their own synthetic data within the UK portal. So this diagram is showing the overview of the framework, starting from the pre-processing of the original data set to generating synthetic data using different kinds of AI model, as well as the evaluation bit, metrics, and also visualizing this evaluations. So the pre-processing aspect involves generating metadata, having a predefined constraint, also be able to define the data sample, but also the predictor column, and how to deal with categorical columns, and also adding noise to input data. So talking about identifying metadata, it's a very important step because this will ensure that the generated synthetic data accurately reflects the structure or the type of the real data set it's trying to simulate or copy. Also, introducing small variation into the data set, kind of like protect sensitive information about the original data set to prevent having the exact replica of the original data set when being generated as synthetic data. Also, because of this variation that has been introduced, there could be little changes in the data set itself. So it's important to have some sort of a predefined constraint or condition or rules that you want some aspect or some variables to follow. For instance, the age variable, you want the age range to be between 0 to 100, or if you have binary columns, you want them to remain as binary, or positive values to remain as positive, or negative values to remain as negative. Also, when it comes to the model computation, for large data sets, kind of like very slow in training this model. And for us, we're using GPU to kind of like speed up this computation and ensure the efficiency when generating the large synthetic data. So talking about generation methodology, there are two commonly used methods, the generative adversary network GAN and variational autoencoders. The GAN models are machine learning models that automatically kind of like learn the patterns or regularity of the input data. And there are two parts of it. The first part is the generator that is responsible for creating this new data set. And the discriminator is just to ensure kind of like a balance to be sure that what is being generated is real. And for the variational autoencoder, this is a probability model that learns the entire input data representation. It also has two aspects with the encoder. The encoder is the one learning this representation of the input data, while the decoder is the one generating the new data based on this representation that has been learned by the model. So this part of the diagram is just showing the various models that has been used in this case for generating synthetic data and the preprocessing stage as well. So for the generative model, there are other variations like differentially private generative models. Because of the issue of AI models overfitting to training data, and this raised concern in terms of privacy when applied to sensitive data set. So the differentially private generative model kind of like had noise to its training weights to ensure to ensure sensitive information are not being inferred from the trained data set. And there are three main important parameters for these AI models. The epsilon value. The epsilon parameter measures the privacy loss in the system, and having a smaller value would mean you're guaranteed to have a better privacy. And for the delta parameter, this is kind of like balance the case whereby the privacy set by the epsilon value might not be guaranteed. So this would ensure that kind of like limits any chances of additional information leakage. The lambda is not all the differentially private generative model uses the lambda, but it's also kind of like a very good parameter that ensures balance in terms of the amount of noise that is being added to ensure privacy. So this diagram is just showing the optimization part of the framework to have the automated, to kind of like have to be able to like automatically find the right parameters for this generative model. And it's also to find the right parameters for this generative model. The optimization bit kind of like does this automatically. So and one of the challenge is being able to find the right balance between ensuring that you have the appropriate noise added to this generative model to ensure privacy, and as well you want to have a good fidelity, a good quality of the generated synthetic data. So this part of optimization kind of like help us to automatically find the right values for the synthetic model parameters. Thank you.
Thank you,
Yeah,
Kathy.
thank you. That's it.
Great. So before we go on to the discussions, I'm just going to give another brief presentation on how we can evaluate synthetic data and what some of the metrics we can use for measuring things like quality and privacy in synthetic data. Okay, so Kafia briefly mentioned the framework that we've been developing within Deep UK, and I'll briefly go through this now to give a bit of a background to that. So we've developed an application within Deep UK where users are able to upload data into this application, which we then automatically generate metadata from, so that we can identify which columns are categorical, numerical, discrete, continuous, to be able to use in the generation process. Then we have lots of different generative methods which users can select from. We have general purpose ones, which are more better at the utility aspect in synthetic data. Or we have privacy focused, which are those differentially private versions of the models, which are better at preserving privacy in the synthetic data. And so these can be selected, and there's descriptions here explaining the differences between these. Then comes the data setup and model setup. So automatically the automatic choice is the PATE CT GAN model, which is a differentially private version of a GAN model. And so it requests additional parameters, as Kafiat mentioned, like the epsilon value, delta, and lambda. And these allow us to control the differentially private parameters of the model to ensure that it can preserve privacy in the synthetic data. Now, it really depends on the type of data that you're using. We don't have standard thresholds for these parameters. They have to be tested on the data that you're using. But you can adjust these parameters and see how it affects the level of synthetic data that's generated. For the purposes of evaluation as well, we ask for a prediction column so that we can evaluate the utility of the synthetic data in an AI model classification task. We'll also ask for sensitive columns and key attributes. So the key attributes are features that an attacker might know who's trying to identify someone. And we can use these to help the differentially private models to be able to preserve privacy, so that it makes it more difficult to be able to infer attributes about a person using this information, and ensures that the synthetic data is private. And then we can generate data where we can then download the synthesizer or the data. And we can see in this specific example, just looking at a subset of the data generated, because age was selected as a key feature, there was one specific instance of an age of 102, which of course is very unique and identifiable because there's only one instance of that. So it generated more synthetic data around that outlier to ensure that there was privacy around that. So it was more difficult to be able to infer the attributes about that person. And then we have a report evaluation, which is generated based on the different metrics that we evaluate for the synthetic data. So we have here on the left-hand side, whole table evaluations, which measure the whole quality, privacy, and utility of the data as a whole. And we can combine these scores to get, the fidelity score, utility score, and privacy score. So we can use this to give an overview of the quality of the data and whether it may be private enough or not. Then if we want to go into more details, we can view the column-specific evaluation metrics. So if we wanted to look at something like the similarity, we can see which features are more or less similar to the original data. And this can help us flag certain vulnerabilities to privacy. So, some features might not matter if it's very similar, but if that feature is a key feature that somebody might know, then if that's very similar, then we might have concerns about that. So this allows us to go into a deeper evaluation of the synthetic data that's been generated. So to measure quality, these are generally the evaluation metrics that can be used to measure that. So the first one of these is boundary adherence. So if we've got in the age column ages between 20 and 80, then we want to make sure that in our synthetic data, the values that have been generated are within those bounds. There's nothing below or above what's in the real data set. So we don't have anything like an age of 198. We also want to make sure that there's range coverage. So within those values that have been generated, we want to make sure that they cover the whole range of values in the real data. So if we have ages 20 to 80, we want to make sure we're meeting all of those values instead of just doing 20 to 40. We want to make sure we're covering adequately the whole range of values within that. We can also compare the shapes or distributions of the features to see whether those distributions have kept relatively the same or whether those distributions have lost any meaning in the synthetic data. And in very private synthetic data sets, we often see more data around the tails of the distribution because it's trying to increase the samples of those kind of more identifiable samples. Then we can look at things like similarity. So we can do statistic similarity to compare whether the summary statistics may be the same or roughly the same. So if we wanted to know the mean of a particular attribute, we can compare whether that's fairly similar to what we would retrieve in the real data set or not. And the same for correlations. We can look at how similar the trends are of the features for two different attributes in the data set to see whether these things match or whether there's been a loss in this correlation when we've generated the synthetic data. And we can also use AI techniques to be able to detect whether we can differentiate between real and synthetic samples. Now, in a normal generative adversarial network model, the main point of the discriminator is to make sure you can't tell the difference between the real and synthetic samples. So when you get really good utility, you can't really tell the difference between them. But when we have high privacy data, then we might be able to differentiate the differences between the real and synthetic. Then to measure the utility of the synthetic data, we can use some of the quality metrics. So again, the statistic and correlation similarity, because these allow us to see whether the data actually has utility in performing certain analysis. But what we can also do is we can test the efficacy of a machine learning model on the synthetic data. So what we would do is we would train the AI model on the synthetic data and then test it on a holdout data set, which is separate to what's been used to train the model, to be able to evaluate its performance and see whether it's able to actually perform well compared to if we were to use the real data to train the model. So this allows us to see how useful the synthetic data is in an AI model performance. And what we can also do, because in this ML efficacy part, we tend to use decision tree-based models. So we can also get the feature importances of which attributes in that data set have a higher influence on the prediction of a certain attribute. So if age is of really high importance in a classification task in the real data set, but it's not in the synthetic data set, then something's gone wrong with that attribute because that correlation no longer exists. So we can measure the differences between the feature importances of what we would get on a model trained on the real data versus what we would get on a model trained on the synthetic data to be able to evaluate whether we get the same sort of feature importances. So these two aspects are really crucial if we want to generate high utility synthetic data for preserving privacy in AI models, for example. Now, the key attributes that the key metrics that we'll be looking at today are these privacy metrics. Now, in GDPR and data protection, to be able to have data which is fully anonymized, it usually has to adhere to these three principles so that the data can not be so that individuals can't be singled out, inferred, or linked. So we'll go through a bit more in detail of what these mean later on. And we also have these other metrics which we can use, so measuring the similarity and whether there's any exact matches in that data. So if we look at singling out, first of all, this basically means there's only one person with attributes X, Y, and Z. So this is something we've talked about before. If an individual is highly unique within a data set, then they can be singled out because there are very unique attributes about them, which means that they can be differentiated from the rest of the data set. And this risk increases with the more attributes that you have about a person. And this is why data minimization is really important as well when we're doing analysis. We want to make sure we're only using the adequate amount of data necessary for our analysis and that we're not using more than necessary, because this can increase that singling out risk. Now, what's typically done in data anonymization practices to avoid the singling out risk is something called k-anonymity. And this essentially offers safety in numbers, where combinations of attributes occur at least k times in the sensitive data set. Now, this usually happens by generalizing and suppressing the data until k-anonymity is achieved. And so we get a data which is kind of transformed into this, where we don't really want, because it hasn't really got very good utility. And it's not very good for preserving the usefulness of the data, as we're generalizing a lot of the data, so we lose a lot of the important data that we need. But in synthetic data generation methods, we can achieve k-anonymity without doing this generalization and suppressing. As in the synthetic data set, it can describe groups of k or more individuals in the original data set. So instead of using this generalization and suppression, we can use in our generation methods, methods to ensure that the synthetic samples represent k or more individuals. We also have inference risks. So this may be to infer attributes about an individual. So if a person with attributes X and Y, we're able to infer whether they also have Z. And we can also infer things like membership. Now, this is something we commonly use in AI models to determine whether they're private enough or not. So if you already know some attributes about a person, such as their age and gender, and maybe some other similar attributes about them, you can use these to be able to target an AI model and query it with the random combinations of the data that you don't know, to be able to observe the confidence score of the model and determine whether the attributes that you're using for the unknown are likely to link to an individual within the data set. And so it's a typical problem in AI models that if you get a very high confidence score, it most likely means it's seen that sample in its training set before. So if you can identify a very high confidence score with some combinations of attributes, then it means that we've been able to identify someone. So we can also do this with synthetic data by training a machine learning model to predict the sensitive attributes using the synthesized data. So that we can then use the fitted model to predict the sensitive values in the original data set. So we can see if we know some attributes about a person, how can we, what's the likelihood of the unknown attribute being this? We're able to measure that inference risk. With membership inference attacks, again, this is something that we usually see in AI models to measure privacy. And this is used to determine whether a particular data points belong to a training data set or not. So from the synthetic data set, we can take a target and find the likelihood of it belonging to the original training data used to develop the synthesizer. But this risk is entirely reliant on what that training group is. So if your training data set is entirely composed of people with mental health disorders, then if you're able to infer whether somebody's part of that training data set, then you can infer that they've got a mental health disorder. But if this training data set is something like the UK census data, which includes the whole population, then by inferring membership as part of that training data set, you're not actually inferring anything meaningful or any extra information from that, because the whole population is contained within that. So when we're looking at the membership inference risk, we also have to take into consideration what the group of the training data is to actually look at that risk. Then the other one of these metrics is linkability. So measuring the risk of being able to combine data sets to identify an individual. So you may have a data set which on its own may not identify an individual, but you could use some of those attributes in that data set to link to an external data with the same sort of attributes and be able to link them together to increase that identification risk. So in this case, this risk is measured by creating a set of target records and identifying the most similar records within the synthetic data, and considering only a subset of the attributes. Then if the nearest neighbor sets for the target attribute share a common synthetic record, then a link is established. So the risk is calculated by the success rate of establishing these correct links between two data sets. Then we also have nearest neighbor similarity, which is used a lot in synthetic data. So this compares the similarity between real and synthetic data points. So before we train a generative model to create synthetic data, we would usually split the original data out into a training data set and into a holdout data set. So the training data set's used to train the generative model to create the synthetic data. But we have this separate holdout data set which can be used to compare with the synthetic data, which hasn't been influenced in the generation process of the data. So typically, when we look at the similarity of these data points, if the holdout data and synthetic data are just as close, then that means that there's maximum privacy and the utility is preserved. If we get the case where the synthetic data is closer to the training data compared to the holdout data set, then this means privacy is compromised because that synthetic data is much more similar to the training data set, which means it has encoded some of that original information within it, which means it's more likely to be able to identify real people within that data set. And then, the other way around, if we have the holdout data closer to the training data set compared to the synthetic, then this means utility is compromised. It means that the synthetic data is so far removed from what the original data is that it's no longer usable or useful for performing analysis. So when we're generating synthetic data for all of our synthetic data points, we can measure the similarity between the training and the holdout data sets. And what we ideally want to achieve is this 50-50 split, where we have 50% of the data closer to the training and 50% closer to the holdout. And this means that we've got a good balance between privacy and utility. What we don't want is cases where there's more samples which are closer to the training data set, because this then means that the privacy has been compromised because a lot of those synthetic samples are closer to the original data, which again, we don't really want. And finally, we have exact matches. So this is a really simple evaluation metric just to see how novel the synthetic data is compared to the real data. So just checks to see whether there's any exact matches between the synthetic and the real. And we can adjust the parameters as well to check for slight variations in this as well. So it doesn't have to match exactly, but within certain bounds. So those are the evaluation metrics. And before I finish, I just want to briefly talk about differential privacy, as it's been talked about a bit before, about creating differentially private models. But what is differential privacy? Well, differential privacy is typically used to ensure that no one individual record on its own could influence the effect of the analysis. So if we have participant X, if we have an input data with participant X's information and we perform some analysis or computation to get a result, then we measure the difference between performing the same analysis but on data without participant X's information. And so epsilon is this difference between the results. And ideally, in differential privacy, the outcome should be the same with or without this participant's information. If there is a difference between the results, then it means that we've got that participant's information encoded, which we don't want, because we want to know the general patterns of the population rather than the individual characteristics. And there's typically two ways of achieving differential privacy. We have global and we have local. So in local differential privacy, noise is added to the data stage before performing any analysis or computations. And then we have global differential privacy, which is added during that kind of computation stage to provide private answers. Now, in differentially private generative models, we can use differential privacy to be able to add noise into the process. So we can either add noise to the data stage or add noise during the training process. And it's much better to add the noise during the training process. So to guarantee the privacy of the generator, noise is added to the gradients of the discriminator during that training to create a differentially private discriminator. So we can use these differentially private models to be able to create these more private data sets rather than typical generative methods. So when we're looking at generating private synthetic data, we want to be using these differentially private versions as they ensure privacy a lot more than typical methods. So hopefully that gives you an overview of what the evaluation metrics are in synthetic data and how we can ensure that synthetic data is private enough, but also is useful enough. And we'll now be going into a discussion where we'll talk about these points in a bit more detail and discuss how we can actually use these evaluation metrics and whether they're enough to be able to determine things like privacy and utility in synthetic data.